All right, welcome. In this video, we're going to take a look at Huffman trees and how they're used in the Huffman encoding algorithm. Before we look at Huffman encoding in more detail, I just want to talk a little bit about encoding data in general. Normally, when we want to store data in memory or in the machine, we have to encode it in binary. And most of the data that we're used to storing in the machine have very standard ways of encoding them in binary, so much so that we might sort of forget they're there at times, or maybe we know a little bit about how each of these data types are already stored in memory. Integers are, well, natural numbers, more precisely, are probably the easiest data type to imagine encoding in binary, because we can translate the number into binary, into base 2, and simply write it in base 2. Now this works really well for, like I said, natural numbers, because they don't have any sign, or at least the sign, the positive sign, the plus sign, is just assumed. And so when we encode them, we assume that if we write 101, we assume that means plus 5. Even integers aren't simply encoded as just their binary equivalents. The negative integers, we have to deal with how do we handle the sign. And then once we introduce the idea of 2's complement for negative integers, we've also implied a bit width for our integers. That is, we only allow integers to have a specific number of bits. We are probably used in most programming languages, modern programming languages, that a standard integer is usually about a 32-bit stored value, which ranging from negatives to positive gives us, again, 4 billion rather in range, or about from minus 2 billion to positive 2 billion. Or of course, if we have a long, then that's 2 to the 64, which is considerably larger. A lot of our calculations can be carried out in that space. So once we've assumed that bit width of 32 or 64, we can encode negatives using their 2's complement. And we're not going to talk too much about that here, but remember the benefit of using 2's complement when we encode negatives is that if we want to actually compute the subtraction of the two values, we merely have to do the actual bitwise addition, ignoring the carry, the overflow, that is, and that will compute the appropriate solution to the subtraction problem. And so that makes things useful when trying to compute these operations while our values are encoded in memory in the binary that they're in. Now integers might be the simplest thing to encode in binary. If we want to extend our number base to real numbers, then we use a different kind of expression. We typically call these floating point representation. This involves using a decimal point and an exponent value, very similar to a scientific notation. And this, because this point is this decimal point moves throughout the number, we call this a floating point. So as a result, historically, the type of the data type that we use to represent these real numbers is the type float for floating point. And then you may also encounter, of course, in some modern languages, we call this a double, for actually double stands for double precision floating point. So that's double in the same way that a long is double precision integer. You can think of a double as being this double precision floating point representation. Now, this video, we're going to focus on text and encoding text data. And our standard way of encoding text data is using the ASCII character set, or the Unicode character set for the more extended character set. And all of these encoding systems are sort of straightforward, easy to use, and that's one of the reasons why we actually use them. But every once in a while, we're going to want to switch to an alternative encoding method, usually because there's some purpose or reason why switching to a different encoding is going to be good for us. Usually it makes something more efficient for us. And our focus here, we're going to be talking about data compression. So we want to make the number of bits we use to store something as small as possible. And then able to do that, we might be wanting to do that rather to communicate the message, or maybe store the message. So this became an important thing sort of in the older days when we wanted to store stuff, when we had limited storage. Now storage is a little bit more abundant. But we still sort of go through the practice of zipping things up, compressing them up when we maybe want to store them for a long period of time. But more often, more commonly these days, we might zip something up as a means of shrinking it down for sending it over the internet as, say, an attachment in an email message, or maybe even just a text or some type of SMS message. We could zip the file up and send it in that way to make it smaller, and then therefore make the amount of time and resources spent in communicating it less. So as I mentioned, we're going to focus on text data to start out, and I wanted to start with the original ASCII table, and here I have it displayed for us. The original ASCII table was standardized in the 1970s as a sort of a response to the need for an ease of communication between the sort of newly arising computer world. There were a number of different sort of supercomputers that had been created on different university campuses or corporation campuses around the United States and the world. And of course, when they were designed, they were all sort of special purpose machines. And so they were all just specifically designed by the people intending to use them. And it turned out that it meant that you couldn't move a program from one of these machines to the other easily, or maybe at all. In fact, in these days, programming wasn't even thought of in the same way. There wasn't a program that you could move in that sense. But even, say, a file, say there was an output produced by your program that you would then maybe print or display. Of course, it would be maybe in text, some text coding, but your text coding might be different than someone else's. So here in ASCII, we can see, say, like capital A here is character number 65. Well, maybe in your research partner's lab across the world here, they decided A should be 40. Well, now it just makes it very very hard to translate your text file into my text file. So as a result of this, in response to the demand to have ease of communication, we need to standardize how we decide to encode our text. And like a lot of things in sort of human culture, we just decided to adopt a convention. So even our normal ordering of the alphabet, A, B, C, D, E, F, G, is a conventional ordering. We only order it that way because that's the way the song goes, and if the song didn't go that way, then we wouldn't have ordered it that way. So we can imagine ordering it a different way, and this is different, for instance, than the numbers. The numbers are actually ordered in that way. We can't go 2, 3, 9, 7, 5. That's not the order that they go in. The numbers actually go in the order they do, but we've adopted a conventional ordering for the letters. And then the ASCII table itself is also a conventional ordering that we've adopted. And we can, again, maybe let's just think of ourselves being in the position of these early adopters of the ASCII table. And maybe they had a conference, and this was before my time, so I'm not sure. But imagine they had a conference and they said, okay, what characters do we need to encode? Maybe they just brainstormed it up and they said, okay, Well, let's get the capital and lowercase alphabet characters. We all, it was probably a bunch of English speakers, so they said, yep, those work for us. And then they said, well, a lot of us do math with our work too, so we probably need these characters here as well. And then if we're going to be, writing messages and doing some math, we probably want to include some good punctuation, maybe get some quotes in there. I like to ask questions. Hey, I do some math, so maybe we want to do some division, some multiplication, add the asterisks in there, and a few others. We added some brackets, and so on. And after listing out the number that we have here, let's maybe add them up here. So if we add these guys together, we got 52. There's another 10 here. I don't know how many we did there, but it looks like another 10. Let's say 20 for good measure. Where are we here? Where it looks like we're at about 82 characters in our list. Now, what I want to start thinking about when we're doing our encoding here is if we have 82 characters, how many bits do we need to encode that many characters? Okay, let's just go, sort of simply here. Let's say I just had these characters, A, B, and C. How many bits do I need to encode these characters? Well, I can try. I might try only using 1 bit, but after encoding A and B, I don't have any values left for C, so that's not enough. 1 bit is not enough. I can still assign A to be 0, and B to be 1, and then I can make C 2 if I use 2 bits, and in fact that would leave me 1 code word left over, so I could also encode, say, D if I wanted, if I use 2 bits. And of course if I add 1 more bit now, so this is 4, which is 2 squared. If I add 1 more bit, I'd be able to do 8, which is 2 cubed. So, using that same sort of idea and the logic here, we say, okay, how many bits do I need if I wanted to do 82 characters? Well, we kind of need to do the inverse calculation of this exponential function, which is the logarithmic function. And so really what I want to know is what log base 2, well, let's grab my number here, my estimate here, 82. So what's that? Now, I don't know what that is. And, some of us, our instinct here might be, let's go grab a calculator, let's go punch it in and see what it's equal to. But we don't really need to know exactly what that value is. It's going to be something, point something, something, something. I don't really care about the something, something, something. In fact, I probably either need the ceiling or the floor of this. So how am I going to know? Well, if I took the floor, that would mean I could actually hold less than 82 characters probably. I want to be able to hold 82 characters and have room for maybe more. So I probably need the ceiling of this instead. And if I want the ceiling of this, what that means is I'm looking for a power of 2, the next power of 2, the next one up. Well, 82 is squarely between 64 and 128. So it looks like 128 is the next power up. Or another way of saying that, what's 128? 128 is 2 to the 7. So it looks like I need 7 bits to encode my 82 characters. Okay, so we did a little math. Imagine we were at the conference with some others, talking about how many characters should we encode. And we got it down and we said, we have 82, maybe we just agreed on a few. And so we said, fine, we'll just throw in anyone that anyone thought was good. And it turned out we did pretty good. We got, space, and here we got the number sign. Some people said, how about a dollar sign, these ampersand, so on. Maybe we forgot a couple, greater than, less than, all the way through here. All these characters make sense. A couple different kinds of brackets, a vertical bar. And then what we'll notice is outside this set, these are all what we sometimes call the printable characters. There are also characters that are not printable. And maybe this last one here, delete, is a good example of that. Delete doesn't print a character, it actually deletes a character. So when you press that key on your keyboard, it sends this signal, and that produces not a character like pressing an S would make an S. It deletes a character, which is sort of a special case. In that same case, there's going to be a lot of other special characters over here that we use that do not produce a character at all. A lot of these special characters were very important in 1970s, but are not very important anymore, but are still, these slots are still sort of used for backward compatibility purposes. Again, some of these are important, but some of them not so much. So let's take a look at a couple in particular. One that is still used because we use it in a lot of code is the null character. The null character is just the character number 0, and it again has no printed value, but it's also has no functional value most of the time, with the exception, or one clear exception, is that we'll sometimes use the null character to terminate strings or terminate strings in C. That's very common. So the null character might be used as as just sort of a symbol or a signal, just as the null value is used in many programming languages when we need a null version of a character. So that's character 0. We've got some sort of start and end of messages and texts that can be used. There's also going to be versions of that for the files, so there's a file separator here as well. But maybe in here there are a couple other important ones that we still use. So like the delete we saw below here, we have the backspace. Okay, we have tab. That's one we still use. Vertical tab, that's slightly different. We have line feed and vertical tab. These are slightly different values, and we also have this carriage return value. These different values, that some of them seem like they maybe do the same value. Let's maybe focus on line feed and carriage return. This goes back to having old-fashioned typewriters before modern computers were abundant. And when you were typing on a typewriter, when you got to the end of a line, there were actually two functions that you needed to perform while you were typing. One was you needed to sort of roll the paper up to the next line, and that was called sort of your line feed. And then you had to return the carriage, whatever that is. You had to basically push the cursor back to the beginning of the line. So there's sort of two operations. And in early computer science, when we were building these early text editors and so on, because most of the people were trained on typewriters, they thought of these two operations as two separate things, because they were two separate things for typewriters. But we obviously, in modern days, think of these as just one thing. When you get to the end of the line, you press enter. We might think of this as enter now. You get to the end of the line, you press enter, and it brings you to the beginning of the new line, all in one step. So again, this is sort of a conventional, hangover from an older time, where we have these different values here, and actually some of you probably are already familiar with this, that there's a difference between encoding text files today between Windows file systems and Unix, or Apple uses a Unix system as well. But when you're shifting between these two systems, I think I might get this wrong now, but I think Windows has two of these characters still in the old-fashioned way, and Unix only has one, or vice versa. I maybe got that mixed up. All that I can remember is that when I switch from one to the other, they usually send you a little message, and going from one way to the other, you're gonna either see all of your lines all on one line, because it looks like you're missing out on one of these characters, or in the other, when you switch back the other way, where you take two characters into a system that only expects one, you'll sometimes get an extra character showing up at the end of every line, and sometimes it's an unknown character. Okay, so that's again a couple special characters in here. Some of these are really special characters that probably never get used anymore. This character number 7, when I was 10 and 11, it was my favorite character, because if you read it, it would make your computer go beep, and at that time, that was the only sound my computer could make. It didn't have any speakers or anything. So if I wanted it to make a noise, I could just print character 7 and it would make a beep. Probably not very useful anymore. But all of these ones up front here are non-printable characters, and so you won't see them. Okay, moving past this ASCII, you'll notice this ASCII, we did the math and we said, well, if we had 7 bits, we could store 128 characters. So this was the original table. Now, it wasn't too long after this table was created that they said, you know, people put up their hands and say, hey, wait, you forgot a few characters. Maybe the English folks said, hey, we got the $ in there, can we get the pound symbol? Okay, all right, fine, we'll put the pound symbol in there. And then, a few other currencies lined up behind that and said, hey, what about us? And while you're at it, said, some of the European languages, hey, we use your alphabet, but we put accents on some of our stuff. Can we get some of those accents thrown in there for our languages? Sure. Okay. And then actually at the time, the first emojis were added to the character set too. This was not well known, but in the 1980s, we did have a smiley face. So we had a smiley face that we could put in there. They were probably running out of characters at that point. And then actually they put a whole bunch of other interesting characters in, some of which you may have seen before. But they have interesting shapes. Let's see if I can draw a couple here. They look like, like this, or like, no, well, that's an equal sign. But like this. The idea is you could take these things and you could put them together, and with some of our other symbols, you could make menu-like looking objects. And this was important back in the days of DOS, and again in Unix in these early days. Before you had your Windows, you had menus that looked like this, built out of this stuff. Now we don't use that stuff for very much anymore, except for what's now a new kind of art form. Well, it's not so new anymore, but it's still popular, which is ASCII art, where you can draw pictures of Pikachu or whatnot, built out of all of these different symbols. And so those symbols still get used today in those types of artwork, but aren't used for very much other than that. You can find all those symbols in what's called the extended ASCII table, which extends this 1 extra bit, taking it to 8 bits, which doubles up the space, got a whole bunch of new characters in it, and that was the most useful character set for a couple decades before we got to saying, hey, well, why don't we try and expand our character set to be truly global and incorporate all of the character sets of all of the languages in the world, and then once we've got some extra space in there, hey, let's throw a couple thousand emojis in there. We've got a whole bunch of emojis we want to put in there as well. And of course that extended set is called Unicode, and I'm not going to say too much more about that, but that's a little history of encoding data. Now, one upside or maybe downside as a result of this type of encoding is you'll notice that there are a lot of characters that we don't use anymore, and they're taking up primo spots right at the beginning of our encoding. These are 0 to 32 here. These are some good spots, right? As a result, that means if we've got a bunch of characters in there that we don't use, it means our encoding scheme is not very efficient. It's not spending those bits very well. That's maybe one whole bit worth of data that we could delete out if we just nowadays could modernize things. Unfortunately, we're not going to be able to do that, but if we have a means, or rather a need, to try and compress our data down, we need to shrink it down for storage or for communication, then maybe we'll say, hey, for the time being, we'll translate it out of ASCII. ASCII, remember, is just really easy to read. You can send it anywhere and anyone can read it, but maybe for the time being we'll shrink it down, take it out of ASCII, and then as soon as someone needs to read it again, we'll just blow it back up again to its original size. So that's what we're going to look at here, and let's think of maybe the message that we want to send here. This is just an example message. Anna has a banana in a bandana. Now I've carefully selected this message because it has a few properties that make it good for compression. One is it uses a small number of characters. As it says here, I only use 8 characters. So that's going to be helpful in our Huffman compression, which is what we're about to take on. And then in a later video, I'm going to take a look at another kind of compression that makes use of repeated character sequences. So in this case, the sequence AN and NA appear many times, and as a result, that's going to also contribute to some good compression. All right, so we're going to use this as our example. I also just want to remind you that a set of characters in this context is usually called an alphabet. So just like we did with ASCII, let's say we were sitting around saying, how do we encode this message as small as possible? Well, ASCII uses 8 bits per character. That's maybe a little bit wasteful. What if I only wanted to encode these 8 characters? Well, using that same math, doing log base 2 of 8, the ceiling, if we want, is still log base 2 of 8 because 8 is a power of 2. We find that it's 3. We only need 3 bits. So here I have a possible encoding scheme where we have 3-bit code words assigned to each character. So again, I've just thrown the characters in here: A, B, D, H, I, N, S, and space. But then I've iterated through my 8 possible 3-bit code words, just basically counting through the binary equivalent of 0, 1, 2, 3, 2, all the way up to 7. All right, so this is one possible way that we could encode our message. We might note here that our message actually has 30 characters in it. So with 3 bits per character, if we encode this up, we'll get ourselves a 90-bit string. Now, our normal way for encoding would be ASCII. And actually, one of the benefits for using ASCII, as I sort of mentioned in the motivation there, is that we don't need to send the ASCII table along. We don't need to tell, this isn't a secret coded message. We don't need to tell the person on the other end the secret code. This is a public code. Everyone knows this code. So we're expecting it to come in ASCII. So you send me a text file, I'll read it straight up in ASCII. Only if it's in a different encoding scheme, like this one we just came up with, would I have to tell you what the encoding scheme is. Now, if I encoded this message using this encoding scheme, you wouldn't know what it is. If I just send you a string of bits, your instinct would be to think it's ASCII, but you'd take this 90 bits and it's not even divisible by 8, so it's not even a full number of characters. But even if you tried to encode it, you'd get some garbage probably. So instead here, again, the benefit of ASCII is you don't need to send the directory along, but if you want to encode it with those 3 code messages, we have to send that along. Now, let's do a couple of calculations here. Our first one here is using ASCII. We would have, again, our 30 characters times 8 bits each. ASCII, we're using extended ASCII with 8 bits. That's going to be 240 bits. Now 90 bits is considerably smaller. This fraction reduces to 3/8, or about 37.5%. This is actually pretty good compression. It's pretty rare to have that good a compression even for text file. Text is a very wasteful, ASCII and Unicode are very wasteful ways of storing text. So you can usually get some pretty good compression on them. But even this is maybe a little bit abnormal or unusual, and that's probably because I carefully crafted this string to have a good compressibility for our example. Okay, so I mentioned though, if we really were going to compress this using our 90-bit code, if we just send them those 90 bits, they wouldn't know what to do with them. They don't know what that is. It would be garbage. So if you've compressed it into garbage, you haven't really done anything. You have to be able to decompress it somehow. So I do want to think for a moment. Let's think about how could we send them a message to help them decode this. Well, what we could do is we could send them our directory. That is, send them each character and the code word that's assigned to it. And maybe if we're a little bit clever, we'll realize, hey, I don't need to actually send the code word. I could just send the characters in order that I encode them, assuming my decoder is going to say, okay, the first one will be character 0, the second one will be character 1, and so on. So they put them in the same order as us. So that means I just need to send each character I'm encoding. Well, how am I going to send the characters? Well, something that you already know, ASCII. Something that you already know, ASCII. Okay? And since we're gonna send them in ASCII, those ones are gonna take 8 bits. So let's say again we had our characters, we had 8 unique characters. Each one's going to be 8 bits long in our directory. That's 64 bits. Even still, our total 154 bits is less than 120, or sorry, it's less than 240, and therefore we get a compression ratio here calculated to be 64.2. All right, now typically here I've sort of put in some effort to calculate the size of the directory, which is worthwhile, at least for our example, but typically the directory is usually very small. Here I've got a very short message with only 30 characters in it. Even, you know, some of the shortest emails probably have 200 characters in them. Usually the directory is, you know, is very small compared to the size of the actual message, and so we'll usually ignore it. Usually its size is not worth considering in our calculation of compression. Okay, so this is David Huffman. He's who we are crediting the work for the Huffman compression algorithm to. David Huffman was a computer scientist. He actually famously solved this problem during his PhD in the 1950s. And this is sort of an interesting and cool story. It's also sort of interesting to talk a little bit about the nature of computer science in this time. Again, in the 50s, there weren't very many computers. Most computer scientists were actually mathematicians or electrical engineers of some kind or some other kind of engineer. And so he was assigned during his PhD, as a part of getting a PhD, you usually have to take an exam of some kind, and he was given the choice of either writing what was called a term paper or taking this exam. And his supervisor at the time said, okay, well, he said, I want to write a time paper. So his supervisor said, all right, here's your topic. Go find me the most efficient binary code. So Huffman's like, all right, did some research, looked at a couple codes, even some codes due to his supervisor, and found, well, none of these are the most efficient. And he was about to give up and say, okay, I'm going to go take the test then. What's the test? But as he was doing that, he thought, well, maybe if I put the codes into this sort of binary tree structure, and that might help me minimize the codes for, well, importantly, the most frequent characters. So in fact, his algorithm relies on something called a frequency sorted binary tree. That's what we're going to look at next. And he uses it to assign short codes to characters that we use a lot, and long codes to infrequently used characters. So this idea that he uses is actually tied back to another very important piece of theory, mathematical theory, the founding of what's called information theory by Claude Shannon, shortly before this time, where Huffman was working on this. So he was aware of Shannon's work, and he was trying to work with Shannon's work to find these most efficient binary codes. And the work of Huffman and Shannon has actually rippled through computer science, but it's also into popular media and popular science, where popular games like Wheel of Fortune or Scrabble or Words with Friends and so on, these games that rely on the frequency of the frequency of characters in for English speakers, English words. So for instance, we know that vowels occur more frequently than consonants, and then among the consonants there are some popular consonants, R, S, T, L, N, and E. These are some popular ones. You get these ones for free. So Again, if you look in Scrabble at the point values, the Q and the Z have the highest points because they're hard to put in words. Vowels have the least. So you can use this information in different areas, but Huffman's idea was to use it to compress. So let's see how he did that. So we're going to start by just looking at a couple different kinds of encoding schemes. So first of all, I've already been using this terminology, but the binary code that we assign to each character, we'll call a code or a code word or a word. And so I've been using that terminology already, so hopefully you've noticed that. And we're going to use that idea here to define a couple different kinds of codes we might come up with. Now, the ASCII code, the Unicode, and this 3-bit code that we've looked at so far, these are all examples of fixed length code where every code word is of the same length. So every character gets assigned an 8-bit code in ASCII, or 7 in the original ASCII, or 3 bits in our version, or one of the variable lengths of Unicode, 16, 32, and so on. The reason we like fixed length codes is it makes decoding very simple. If I want to decode ASCII, if you send me a string of bits, I grab the first 8, look it up on the table, and there you go. That's my character. I'm done. Grab the next 8. Grab the next 8. Always blocks of 8. Always blocks of 3 if we're in our 3-bit code. Always blocks of 16 or 32 if we need to in Unicode. And so because of that, we default to fixed length codes. If we have a choice, why not? It's easier. A variable length code then assigns code words of potentially different lengths to each character. Now, of course, this makes decoding a little bit problematic because now when you send me that string of bits, I don't know how many bits I need to grab to decode the next word. If you have code words some of length 5, 6, 7, and 8, how do I know? Do I grab 5 bits, 6 bits, 7 bits, 8 bits? Some variable length codes might just do trial and error. I'll try 5, look it up. Is it in there? Okay. If not, move on to 6, and so on. Others will have techniques. Huffman's creates a variable length code, and it has a technique for making sure it knows how long a chunk to read off of a decoded message. One problem with variable length codes is that they can be ambiguous. And again, this is a problem with decoding. So let's take a look at this variable length code here, where A is encoded as 0, B is encoded as 1, and C is encoded as 0, 1. Now imagine receiving the message 0, 1. This message is ambiguous in the sense that it could encode the message AB, or it could encode the message C. And so it's ambiguous because we don't know which one it is, and therefore it's impossible to decode. A code is called prefix free if no code word is the prefix of another. So the unfortunate problem with that code above there is the code word for A is a prefix for the code word for C, and that introduces ambiguity into the code. That's what makes it a problem. When we see the 0, we don't know if that's encoding an A or if it's encoding the first bit of the C. If, on the other hand, a code is prefix free, we won't encounter this problem. We'll never encounter this problem, in fact, if no code word is the prefix of another. And so we will not have this ambiguity in decoding, and it will enable us to make decoding possible. And luckily for us, Huffman's algorithm will always create these prefix-free codes. Okay, so let's take a look at Huffman's actual algorithm. So Huffman's algorithm has 5 main steps, and I've got it stated here in pseudocode, but I'm going to talk about each step in turn. So here I've got the first one. Since Huffman wants to assign short codes to most frequent characters and long codes to the less frequent ones, we need to count the frequency of characters. So that's the first step. As I mentioned here, we're going to do that with a single pass over the characters, and we'll typically use a map or a map-like structure to store the frequency of each character, so that this is done with most efficiency or order n in the total pass. So step 1 takes big O of n, where n is the number of characters in the message. All right, so now for each of the characters in the message in step 2, we're going to create a tree. Now, the initial tree that we create is actually going to be a single node, so it's sort of a degenerate tree, and then it's got a single node, and we're gonna store the character right in that node, and then we're gonna weight that tree, not the node, but the tree itself, with a weight which is equal to the character's count. Now in this step, we have to create each one of these trees. We assume that the creation of the tree is only going to take a constant amount of effort, so it depends on how many trees we need to create. So the number of operations carried out by this step then is dominated by the number of unique characters in the whole message, not the number of total characters in the message, just the number of unique characters in the message. And so I'm going to call this D, and so this step's going to take big O of D. Now sometimes I've kind of used D here instead of M or L or something else, because often D is going to be a constant for us, or we're going to know it's a constant. For instance, if we know we're compressing something from ASCII, we already know that the D is bounded above by 256. So we'll often consider this to be big O of 1, in which case we'll start ignoring this step. But for the moment, we'll keep in mind that it could potentially, in the worst case, be equal to n, although that's a really strange, bizarre case. So we're not actually going to assume that in this case. We're actually going to leave it as big O of D for now. So we now have one tree for each unique character, and now we're going to go through this loop. Where in this loop we're going to eliminate one tree at a time. We're going to eliminate it by actually doing this. We're going to pull 2 trees out of whatever data structure we're using, although we'll usually use a priority queue here. We'll pull 2 trees out with minimum weight. We merge them together, and then we put them back in. So the way we're going to do this, how we're going to merge them, is we're going to create a new root node, and the 2 trees we've pulled out, we're going to make the left and right subtrees. It doesn't matter what order. Usually there's some convention when we implement this. And then the new tree is going to get a weight equal to the sum of the weights of the original trees. And after we're done that, we'll put it back in the priority queue. So I mentioned we're usually going to use a priority queue for this step because we're always trying to find trees with minimum weight, and that's what priority queues and min heaps are good for. And so this whole step, which is the loop here, because we started out with D trees, and each one of these iterations we're going to eliminate one of those trees, but in each one we're performing these heap operations, so we're going to get this D log D runtime. Again, if D is a constant, this whole thing's a constant, and we'll ignore this operation. Otherwise, we might leave it as this. All right, next we're going to recover the codes from the tree. Now usually this is going to require a depth first search of the tree, or depth first traversal. When we go down left branches, we're going to record a 0. When we go down right, we're going to record a 1. And then when we encounter a leaf which contains the characters, we're going to just report whatever code we read on the way down. Now the cost of this is the cost of visiting every node in that tree. Now that tree has at most 2D minus 1 nodes in it, or it has exactly 2D minus 1 nodes in it to be exact. So it's order D to visit every single one of them. And again, if D is a constant, we'll ignore this cost as well. So once we're done that step 4, we have all the codes, so now it just remains the cost of encoding the message, which means going through the message one character at a time, encoding it in binary. This is clearly going to take order n again, where n is the number of characters in the whole message, not the number of unique characters. So adding these together, we have a couple steps that are order n, we had a couple steps that were order d, we had one step that was order d log d. So adding them all together, we get this sort of order of n plus d log d. And again, as I mentioned, if our d log d is a constant, we'll just ignore that term and call it big O of n. All right, so I think all that remains is for us to do an example with our example string. So here we have Anna has a banana in a bandana, and we can do step one here, and I've carried it out here in my table. Step one, count the frequency of each character. Don't forget the space here. And so A happens to be our most frequent character with 11, space and N coming in second and third, well, third and second, I guess, with 6 and 7. And then we have a lot with just only a single occurrence, and B with 2. And this is actually true of a lot of data out there. That this is true of this string by design, but it's true of a lot of data. This kind of distribution is sometimes called a power law distribution, where we have sort of a lot of characters with only 1 or 2 occurrences, and then we have a few characters with a lot of occurrences. We see this in a lot of different patterns in the real world, but here again it's by design, and this pattern isn't really anything important to this compression other than that it makes it it makes it compress well using Huffman's algorithm. So let's go ahead and do this. This is step one. Let's do step two, which step two says let's make a tree for each one of these. So here I've gone ahead, think of these as 8 trees. Each tree only has a single node, and I've weighted each tree with the weight, the number of characters, or the number of appearances for that character. Now we're going to do some merging of trees with the minimum weight. So imagine we stuck all these trees in a priority queue, and we ask for it to give us out the 2 with the minimum weight, and we're going to merge them together. Now here we have a tie, we have 4 with minimum weight, so it depends on sort of what order our priority queue is handling them. Now I've gone ahead and assumed we got D and H here first. Now this is sometimes, you know, common if we put them in order maybe we put them in alphabetical order, I'm not sure, in which case when there was a tie they would remain in there in the order they went in. So that was our first step. Now remember, merging them together means creating a new node and making our 2 other trees the left and right, and then summing their weights together. They used to be 1 and 1, now they're 2. Also importantly, the new node has nothing in it. It's sort of a null node. It's just there to connect them together. Okay, next step, we're repeating this until we only have 1 tree. In that step, we eliminated 1 tree in that merger, so we now have 7 trees. Obviously now we have to merge our 2 our I and our S. Okay, so we merge them together. And again, we now have a choice. I've decided to, more for convenience of my slide, to merge these 2 together. Although again, if we were following strict queue rules, it would have probably been the B merged with the DH. I should point out, when we have a tie like that, that means we could end up with different trees. If we ended up with a different tree, we'd get a different set of codes. And if we get a different set of codes, we're going to get different encoding at the end. The one beautiful thing about Huffman's algorithm is it guarantees us that if we follow the algorithm properly, no matter how we break ties, we will get optimal encoding. And another way of saying that is, no matter how we break ties, if we all break ties different ways, we'll all encode down to the same length. And that's going to be important. Again, remember, that's part of it being optimal. If we all didn't compress to the same length, some of us would not be optimal, and the algorithm would not be optimal. Okay, so in this case, we need to continue. Well, it looks like now next is 2 and 4. So we'll merge them together. I've just sort of moved the B up to make it a little easier to draw. The next 2 are 6 and 6. So I'm actually going to move my space over to merge them together. So I merged that one on there. Now this huge tree I've created, we've sort of grown 1 tree, and that's not always how it's going to be, and we'll see that in the next step here, because now the next 2 to merge are 7 and 11. So we merge them together, and then we only have 2 trees left. So the last step is always to merge them together. And if we've done it all right, the weight of our final tree should be however many characters were in our message, since we just added all their frequencies together. So 30, so we did it right. So this tree we're going to use to now come up with code words. Now, I do want to point out a few things about this tree. One is our more frequent characters, A, N, and space. Remember, showing up 11, 7, and 6 times. They're all up at the top of my tree. And these other characters, the S, the I, the H, and the D, that all showed up only one time, are all the way at the bottom here, deep down. So I'm now going to assign code words in this way, meaning the ones up at the top actually end up getting shorter code words. 0, 0, 0, 1, 1, 0. The way we assign the code words here are left branches are zeros, right branches are 1, and we just read the values off as we go. Now think about a depth first search traversal here. We'll go down this side. When we reach the A, we know it was a 0, 0. We record it in our box. Next we'll hit N, we know it's a 0, 1, we'll record it, and so on. So with one traversal of the tree, we'll be able to recover all of the codes and build our table. And this is all we need to build our final code word. I've actually put a little bit of effort here to actually show what that code word is. We can see here, an, space, has, and so on. I've encoded it using the code words that we have listed here. Okay, so our H is a 1, 1, 1, 0, 1, 1, 1, 1, 0, 1. So we can see that it's encoded here, and you could count them up, but you don't have to count them up because we have all the information we need. For instance, we know that character A, the character A only takes 2 bits, and it shows up 11 times. So those 11 A's take 22 bits. Now notice here, think about our 3-bit code. In our 3-bit code, those 11 A's took 33 bits. So because of Huffman's code, we actually saved some bits here. We saved 11 bits, okay? But then look, some of our bits aren't saving. We have 5, 5, 5, 5. But these 5 characters, the D, the H, the I, and the S, all 4 of those characters only show up 4 times. So those 4 characters, that cost us 20 bits. If we had used our 3-bit code, we end up spending 12 extra bits here. So the savings we got on that, on just the A's alone, is what we spent on those 4 ones getting longer, while we didn't count the savings on the N and the space as well. So we got 7 bits and 6-bit savings on those ones. So in total, what do we say? 11 plus 7 plus 6, that's 13, that's 24-bit savings. So we actually get more savings than we spend making these ones long. Why? Because these ones are very infrequent, and these ones are not. Now, I didn't talk about B very much because it was encoded as 3 bits in our scheme. And that means we don't get any savings or any cost to it. It was 3 bits in the old scheme as well. But because of that saving, you can check my math here, we end up with 74 bits instead of, we used 90 bits, remember, in our 3-bit fixed code. So we actually end up here with a better compression ratio. All right, I think that concludes my presentation of Huffman's algorithm and Huffman compression. I think in my next video I might do a quick exercise, just running through another example message for Huffman's algorithm. But in the following video I will present another data compression method called LZW, which uses another sort of technique or trick to compress text data. All right, thanks for watching, and we'll see you in the next video.